Hi everyone, we're now getting into the last topic of the course, and this is graph theory. It's going to be split up into two parts. The first part is going to be on general graph theory, and then the second part is going to be on trees. And this will wrap up the course content. So if you think about what we've done in the course so far, the first part was on basic counting techniques, and this was situated around our basic counting objects. And then we got into some probability, and then we covered some advanced counting techniques. These were recurrence relations and generating functions. And now the last topic of the course is graph theory. This lecture we're just going to introduce some of the basic terminology surrounding graphs and multigraphs, and then we'll also do a few proofs. The key thing to notice with proofs in graph theory is that they are a lot more descriptive than, say, proofs in other areas. Other areas are proofs involving counting techniques, etc., all involved some component of algebra. So we set up equations, we manipulated equations, etc. But in graph theory, we have to construct our proofs using arguments, and it will take a lot of writing. So writing out full sentences, writing out full statements, and describing the situation and the logical flow of the argument. We have to capture in those statements, why something is true, how it follows from the previous steps. And so those are all going to be through a descriptive process. So pay close attention when we start to do some of our examples of proofs, because these are the kinds of things that you will want to be mimicking and extending on homework assignment questions and on assessment questions. All right, so let's dive into graph theory. So we've already introduced what a graph was. That was at the beginning of the course. Now I'm going to introduce what a multigraph is. So a multigraph is a pair of sets, V and E. So we call this collection or pair of sets G. And V is the vertex set, and E is a multiset called the edge set. So what is a multiset? A multiset just means that we are allowed to have multiple elements that are all the same. So for example, if we look down at our example here, 6.1, we've got our edge set here. This tells me that there's an edge between vertex 1 and vertex 2, but we also see that repeated. There's another edge from vertex 1 to vertex 2. That's what we mean by a multiset. It's just allowed to have multiple copies of the same element. So let's get a sketch for what this graph looks like. So we've got vertices 1, 2, 3, and 4. Let's plot those down. So 1, 2, 3, and 4. We'll label those as well. 1, 2, maybe I'll put the 2 out here, 3, and 4. And then we've got edges. What are our edges? Well, we've got the edge 1, 2, and another edge that goes from 1 to 2. These are called parallel edges. So if we have two of the same edge that appears, then they are called parallel edges. And we basically draw them in by drawing one edge from 1 to 2, and then another edge from 1 to 2. So there's our parallel edges drawn. We also have an edge from vertex 2 to vertex 3. We can draw that one in. We also have an edge that goes from 3 to 3. So that's a loop. It starts at 3 and then comes back and returns to 3. So we call that a loop. These are really the only two different things we have in a multigraph that we didn't already have in a graph. So with multigraphs, we are allowed to have parallel edges, and we're also allowed to have loops. So that's what distinguishes a multigraph from just a plain old simple graph. We also have an edge from 3 to 4 and an edge between 4 and 1. And I'll label this one here. This is a loop. And my comment about we've dealt with graphs before. In fact, this is what often are referred to as simple graphs. And those things we've dealt with before are basically, well, they are multigraphs, but we just didn't consider any loops or parallel edges. So we didn't allow loops to occur in our graphs, and we didn't allow there to be multiple edges connecting 2 vertices. And those are what we call our graphs from before. So our graphs, we've just extended now the idea by adding the possibility of having parallel edges and the possibility of having loops. And if we have any graph that has parallel edges and loops, that's what we call a multigraph. So let's go ahead and look at some more terminology. So now we want to talk about what a walk is in a graph. So if we've got a multigraph and we've got 2 vertices, x and y, in that multigraph, then what a walk is, it's just a finite alternating sequence that goes vertex, the starting vertex, x in this case, followed by an edge that connects x to another vertex, x1, and then follow another edge to the next vertex, x2, follow another edge to another vertex, x3, and so on, alternating edges and vertices. So we get edge, vertex, edge, and then we end up at our final vertex. I'm just going to label these first ones. This x vertex I'll call x0, and the ending y vertex I'll call xn. And so now we can read off how many edges there were. There's n plus 1 vertices, because I started going from 0 and I ended at n, and there's exactly n edges. And so we would call this a walk from x to y of length n. So the length of the walk, as it says here, is just the number of edges, and in this case we used n edges. A walk from x to y is called a closed walk if it has more than one edge and the starting and ending vertices are the same. So a closed walk is something that starts at a vertex, ends at the same vertex, and had at least one edge in it. Anything that doesn't satisfy those conditions are what we call an open walk. So otherwise we just call it an open walk. So an open walk is a walk that starts and ends at 2 different vertices. Or an open walk is a walk that has length 0, because a part of our definition of a closed walk is it has to have at least one edge. So that's in our convention down here. A walk can have length 0. In other words, there's no edges. That's what we call a trivial walk. And just reading our definition again closely, a trivial walk has 0 edges, so it doesn't fall into the closed walk category, because to be a closed walk you have to have at least one edge and then start and end at the same spot. So this would be an open walk. So this is just something to note, that a walk of length 0 is a trivial walk and it's open. It's an open walk. Okay, so sometimes these base cases in terms of terminology can get a bit confusing, and so I'm really just pointing this one out to you, saying, hey, if we've got a walk of length 0, it's by definition open. You may say, well, a walk of length 0, there's no edges, so you'd have to start and end at the same vertex, so wouldn't that be closed? Well, no, our definition requires that for it to be a closed walk, you actually have to start at the point, then move away from it before coming back. That would be what a closed walk is. If you start at a point and you don't go anywhere and you're still at that point, then we call that an open walk. So that's basically saying that if it's length 0, it's got to be open. All right, so let's have a look back at our example that we started with. So we had our vertices 1, 2, 3, and 4. And we had parallel edges, a loop at 3, and these couple more edges. And so what could an example of a walk be? Well, let's start at, let's say, vertex 1, and we will travel along. Now I'm going to want to talk about the edges I'm traveling along, so we can label these. So let's call this edge A, this one B, this one C, the loop D, this one E, and this one F. So there's our edge labels. So now if I'm going to consider a walk, for example, I could go from vertex 1, I could travel along edge B to vertex 2, then vertex 2 along edge C to vertex 3, around the loop, and then back along edge C to vertex 2, and maybe I'll just end there, and I'll end at vertex 2. So what we've got here is the walk 1B 2, C, 3, go around loop D back to vertex 3, then along C to vertex 2. And so this is a walk. It's a walk from 1 to 2 of length. And what's our length? Well, our length of our walk is just going to be the number of edges that we travel along. So there's 1, 2, 3, 4 edges. So this is a walk of length 4. And since I started and ended at 2 different spots, it's an open walk. So which is an open walk. So we've got an open walk of length 4. And maybe we could do give an example of a closed walk. Give an example of a 1-to-1 closed walk. So in other words, start at 1, end at 1, and make it a closed walk. So I can't just do I can't do this, for example. I can't go just 1 and then no edge and then say, okay, I'm done, because I started at 1, I didn't use any edge, so I'm ending at 1, because that's not a closed walk. That's a walk of length 0, which by definition is open. So we want a closed walk. So we want to start at 1 and we want to move away from it and then eventually come back. So maybe I'll go along B to 2 and then along A back to 1. So I could go 1, B, 2, A, 1. And this is a closed walk of length 2. So there's a closed walk of length 2, started at 1 and ended at 1. So just a couple of examples to get used to what this terminology is talking about. So walks allow us to talk about how to move around a graph. So we'll continue our definitions. We've now got the definition of a walk. Walks with specific properties get called by other names. So for example, a trail from X to Y is, well, it's a walk. It's an open walk because we're going to assume we don't start and end at the same vertex. We're assuming X is different than Y. But it's a walk that has no repeated edges. That's what we're going to call a trail. So we start at X, we wander around the graph, we walk around the graph, and we end at a different vertex, and we never repeated an edge twice. That's a trail. If we start and end at the same vertex, so it's a closed walk, so it's got length at least 1, and there's no repeated edges, that's what we call a circuit. One thing to note here with these, that there's no repeated edges in these definitions, but we can repeat vertices. There's nothing there that says we can't. So for a trail or a circuit, we're allowed to repeat vertices, we just can't repeat the edges. So let's go ahead and look at our example again. Maybe we'll find some trails and circuits on our graph. So that's 1, 2, 3, 4. We had our parallel edges, and we have our loop at 3. And we'll label our edges again, A, B, C, D, E, and F. And so what would be an example of a trail? Well, we could start at 1, we could go along F, E. I just am not able to repeat an edge, but I can repeat vertices, so I could go along D around the loop, come back to vertex E, and then maybe go up to 2. So what we have is that 1, F, 4, E, and then we're at vertex 3, then we go around the loop back to vertex 3, and then C, and then end at 2. This is a trail from 1 to 2 of length. And how long is it? Well, we can either get it from the diagram by counting edges, or we could just look at our listing here and count our edges. We've got 4 edges there, So it's a trail of length 4. So it's a trail because it's a walk that has no repeated edges. But if we think back to our definitions of paths, because we defined paths very early on in the course, we talked about paths and cycles. Is this a path? Well, in a path, we aren't allowed to repeat vertices. You can think of it as a walk where you're not allowed to repeat a vertex. So in this case, this is not a path. So this is a trail from 1 to 4, or 1 to 2 of length 4. It is not a path since it repeats a vertex. In particular, it repeats vertex 3. But we could modify this. We could say go from 1 along F to 4, along E to 3. And instead of doing the loop, just keep on traveling from 3, go along C to 2. This is a path of length 3 from 1 to 2. So there's an example of a path. There's no repeated vertices. And if you think about this, if you don't repeat a vertex, there's no way you can repeat an edge. So by necessity, a path must be a trail, because a path doesn't have a repeated vertex. So if it did have a repeated edge, well, it would also have to repeat the vertices at the ends of those edges. So a path by necessity is a trail. And what this tells us, at least in this example, is that I had a trail in this graph, and I was able to throw some stuff away from it and reduce it down to a path. And that actually turned out to be a general result. This is our first theorem, theorem 6.1.1. Let G be a multigraph. Let A and B be 2 vertices on it. If there is a trail from A to B, then there is a path from A to B. So if a trail exists, then there, by necessity, must be a path. And we get it in exactly the same way we did that previous example. The previous example, we just threw away those edges that ended up revisiting vertices that we had already encountered, and we just shrunk it down to a path. We threw away one loop in that case. But that's how we can prove this in general. So what we'll do is we'll let T, we know that a trail exists from A to B, so we'll let T be the shortest trail from A to B. Okay, we know such a trail exists. It's given in the statement of the theorem. We want to show a path exists. So we will pick, of all the trails from A to B, we'll pick the shortest one. There could be multiple shortest ones. They could all have the same length, but the idea is we pick the shortest one that has the least number of edges in it. Now what do we do with this? Well, we note that if T has, well, I'll say it this way. If T is a path, what does that mean? I.e., no repeated vertices, so it doesn't have any repeated vertices on it, then we are done. We found a path from A to B. It turned out to be this shortest trail we picked. So then the other, or the flip side of this, is T is not a path. So what if it's not a path? So if it is a path, there's no repeated vertices and we are done. So let's assume T is not a path. That is, it has repeated vertices. Let C be a repeated vertex on T. So T has the form. Okay, so we're just describing what's happening here. If our shortest trail is not a path, then there must be a repeated vertex. Let's call C that repeated vertex. So it has to look like this. We're starting at A. we travel along an edge, we get to another vertex, we travel along an edge, get to another vertex, and so on. And then we get to vertex C, and then we know we're going to travel away from C and come back to it. So we know that we are going to eventually go around some number of edges and vertices and come back to C. And then once we hit C again, then we can continue on traveling until we eventually get to B. So what happens is that there is going to be a sub-circuit, I'll call it. So it's a subgraph of the graph T, the trail, which ends up being a circuit. So it's a sub-circuit at C. So we know this is going to happen. We travel along, we hit C for the first time, we travel some more, come back to C again, and then travel some more and get to B. Now in this drawing, I'm not claiming that all these vertices are distinct from each other. We could be traveling along itself again before we hit our C for the first time, and then looping around, traveling along portions again, and then coming back C eventually. The point is that we've hit C, we go travel some more, we go on a little bit more of a walk, we come back to C again. And so what can we do at this stage? Well, at this stage, remember we were saying that T is the shortest trail from A to B. So I look at this diagram and I say, does this contradict the fact that this trail I've drawn is the shortest trail? And we should be able to say, yeah, it does. Because I could have just started at A and ignored traveling along that red portion and just gone from A to B. So that sub-circuit I could ignore and I still have a trail from A to B. So we've got that T has to have this form. If we remove this sub-circuit from T, we have a shorter trail from A to B. But this is a contradiction because T was supposed to be the shortest. But this contradicts T being the shortest trail. So what does that mean? Well, it means the only assumption we made along the way must have been false. And what we did was we assumed T was not a path. And so that assumption had to be false. So therefore, T must be a path. And we are done. So the shortest trail from A to B, it must be a path. And that's what we're concluding here. And therefore, if there's a trail that exists from A to B, then there must be a shortest one, and that's a path. And so we are done. So that's what I was alluding to at the start of this lecture, was that our arguments, they're going to have to be very descriptive. We're going to have to say exactly what's going on, the assumptions we make. We can support some of our descriptions with drawings as well, because in graph theory we do end up drawing a lot. But this is the typical layout of such a proof in graph theory. So now we'll introduce a little bit more terminology, some definitions here. If G is a multigraph and V is a vertex, then we're going to define what the degree of a vertex is. It's denoted by DEG of V, and it's just the number of edges that are incident to V. Here, we're going to assume that a loop counts as 2 incident edges. So let's just draw an example. Here's a graph. So maybe this is vertex 1, vertex 2, vertex 3. Our edges are going to be, we've got edge from 1 to 2. I've got some parallel edges from 2 to 3. I also have a loop at 3 and an edge from 1 to 3. So there's our graph, our multigraph, because we've got loops and parallel edges here. And then we can ask the questions. What is the degree of vertex 1? What is the degree of vertex 2? What is the degree of vertex 3? By the definition, this is just the number of edges that are incident to the vertex. So if I look at vertex 1, how many edges are incident with it? So in other words, how many edges are coming into it or leaving it, depending on your perspective. How many edges are incident with it? Well, there's exactly 2 edges. So the degree is 2. How about for vertex 2? Well, I've got 1 edge, 2 edge, 3 edges. Think of, in some sense, how many things are poking into that vertex. Just count up the number of things that are poking into it, and that's the degree. So in this case, it's 3. How about vertex 3? Well, we got 1, 2, 3, 4, 5 things poking into it. Now you may argue, hey, why didn't I just completely draw that around and come back around and say, oh, that's only 1 edge that's touching it. It just happens to be touching it at its 2 ends. And that's where this fine print detail comes in. A loop counts as 2 incident edges. So if we just look very closely at the vertex 3, then we see there are 5 things sticking into it. And that's helpful to figure out the degree. Now, why do we define degree in that way, and especially for loops? It's because the next theorem, this turns out to be quite an important theorem that's very useful all throughout graph theory, and it really just follows from how we've defined the degree. So what I'm going to do is I'm just going to notice something here with our example. If I take the degree of 1, add it to the degree of 2, so just these numbers, add it to the degree of 3, what I get is 2 plus 3 plus 5, or in other words 10, and that's precisely twice the number of edges. That's 2 times 5, where 5 is the number of edges. And it's not a surprise that this happens, because if you think about what we've just done here, for every edge, all I've done is said, okay, I've counted these 2 edges by the fact that they are incident with vertex 1. But I also count that edge, that top edge, a second time because it's incident with vertex 2. I count these ones because they're incident with vertex 2. And then I also count these ones again. They're incident with vertex 3 and this one as well. So if we look at how I've drawn it here, all those little yellow markings indicate that I'm counting those edges in terms of their degree for that particular vertex. And what I've done is I've just, for every edge, I've got 2 little yellow markings on it. So I've effectively noticed that every edge contributes a count of 2 to the degrees of the vertex, to the sum of the degrees of all the vertices. So how many little yellow markings are on my diagram? Exactly 2 times the number of edges. And that's all this theorem states down below. And so what we can do is we can just prove this theorem. How are we going to prove it? Well, we're going to just notice exactly what we did up above. We're going to say each edge contributes a count of 1 to the degree of the vertex it is incident to. So each edge contributes the count of 1 to the degree of the vertex it is incident to. In other words, each edge contributes a count of 2 to the sum. So this sum here, the sum of the degrees of the vertices in V. So each edge contributes a count of 2 to that. So therefore, we get our result, that the sum of the degree of V's, as V's range over all the vertices, is precisely twice the number of edges. Okay, and again, it was just our argument here that for every edge, it contributes a count of 1 to the vertex that it's incident with. And so how many yellow markings are in my diagram? That total number of yellow little markings I put in there is exactly the sum of the degrees, but it's exactly also equal to twice the number of edges. All right, so we've got our arguably the most important theorem in graph theory, and that's the degree subformula. We're going to be using it over and over again in larger arguments. The other thing I just want to note is that all the definitions we have for graphs, simple graphs, the graphs that we've covered earlier on in the course, so this notion of subgraph, induced subgraph, spanning subgraph, these all hold equally well for multigraphs as well, the same definitions. Let's continue our definitions a little bit more now. So now we're going to introduce what we mean by a connected graph and its connected components. So we say a graph G is connected if for all pairs of vertices there is a path from one to the other. We could even reduce this a little bit further, and we could just say the weaker condition that for any pair of vertices there is a trail from one to the other. And the idea is that, well, we have a previous result that says if there's a trail from U to V, then there must be a path from U to V. So that's why we might as well just take as our definition there has to be a path from U to V. Because if we just said in the definition that there must exist a trail from U to V, well, we already get that there must be a path as well. So a graph is connected if for any pair of vertices there's a path that connects them. The connected components of G are the maximal connected subgraphs of G. So let's have a look at an example. So I'm going to draw a graph here. So this is going to be our graph G. It's going to look like this. And those are all our vertices, and I can label them as well. So we've got vertex 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then what are our edges? Here's our edges in our graphs. They're going to look like this. And so there's our graph. And we'd like to investigate some of these definitions we've just introduced. So is this graph connected? Well, in order for it to be connected, there must be a path between any two vertices. But I can already see, for example, there's no path connecting 2 to 5. There's no way to get from 2 to 5 using the edges of the graph. They just are not connected to each other. So what we say here is that G is not connected. Okay, so if it's not connected, what are the connected components? What are those subgraphs of G that are connected? And so this piece here, that's a connected subgraph. I can get from any vertex 1, 2, 3, or 4 to any other vertex 1, 2, 3, or 4. So I'll call this C1. This is a connected component. We'll call that C2. And this is a connected component. We'll call that C3. So we've got that G has 3 connected components. And I've labeled them C1, C2, C3. And further, just to discuss a little bit about what this part of the definition that says maximal connected subgraphs. So what if we just consider this subgraph here, 7, 8, 9, and that little triangle. So I'll redraw it down below. So we're going to note that this subgraph, 7, 8, 9, is connected. So why wouldn't I call that a connected component? Well, the reason is it's not maximal. I can make it bigger and still be connected. So that's what this term maximal means in the definition. So this is connected, but not maximal. So it's not the biggest connected subgraph that contains those 3 vertices. This one, 7, 8, 9, 10, 11, is bigger and still connected. So that's what this term maximal is capturing there. Okay, so we can look at a graph and say, oh, is it connected? Well, it's connected if I can get from one vertex to any other vertex. If it's not connected, then I can split it up into its connected components. All right, let's have a look at the next definition. Now we're going to extend out to what we call directed graphs. So a directed graph, or digraph for short, is a pair, again, of vertices and edges. The edges, in this case, they are a collection of ordered pairs of vertices. We draw arrows on the edges to indicate their direction. If the graph is not directed, we say it's an undirected graph. So in this case, the only difference is how the edges are described. You can see they're now written as ordered pairs. We've got the round brackets instead of the set theoretic curly braces, indicating unordered collection of vertices. Now we've got ordered pairs of vertices. So what does this graph look like in this case? We've got 5 vertices. I'll just list them like this. And 1, 2, 3, 4, 5 is how I'll label them. Now, oftentimes when you're just given the vertex set and the edge set, it's not clear what a nice way to lay it out is until you start drawing the edges in and you figure out that, hey, maybe I should move this vertex over there because it makes the picture look nicer. In this case, we'll see that laying our vertices out this way ends up with a picture that looks reasonably nice. So we've got 1, 2. So what that means is that starting at vertex 1, we draw an edge connecting it to vertex 2 in that direction. So we've got an arrow attached to the edge now. And then we've got 2 to 3. And then we've got 3 to 1. 4 to 1. And 3 to 5. And so there's our diagram representing that directed graph. Now, what would be a reason we would want to consider directed graphs? Well, for example, we could have a physical interpretation. The edges represent water flow in pipes. Or flow of traffic on a street or a road. So something where there's something traveling from one vertex to another vertex, and the direction it is allowed to travel along that specific edge has a specific one-way direction. It can only move in that direction. So this is water flow in pipes. You may imagine pipe flows going downhill or something like that, or there's a pump that's pushing the water through these pipes in certain directions, and so we need a direction associated with that. What about our vertices? What could be the interpretation of those? So in the water flow in pipes analogy, these could be junctions. Or in the case of the traffic flow, these could be intersections, where there are lights or something. So there's some physical interpretations of this. That's pretty much all I want to say about directed graphs. We may see them in the odd example or two. That's just why I wanted to introduce the terminology. But we're not going to study them. We're not going to study directed graphs in Macm 201. For all of our examples, we'll assume that edges are undirected. So lastly, I want to talk a little bit about some terminology as you may see it in this class, in any of your readings, and then also in future classes as well, is that graphs are classified as either directed graphs or undirected graphs. We're going to focus on undirected graphs in this course. Simple graphs are graphs with no parallel edges and no loops. So for us, we're not even going to call these simple graphs. These are just going to be called graphs, because if they do have a loop or a parallel edge, then that's what we call a multigraph. So for the most part, you'll never hear me say the word simple graph. Grimaldi in our textbook uses the word simple graph, and it's meant to capture no parallel edges and no loops. But for us, when we say the word graph, there's no reason to add the word simple in front, because that would be redundant. Vertices that are adjacent are also what we call neighboring vertices. Graphs are also called networks. So this is a big one. Depending on which discipline you go into, you may never hear the word graph, but you may be using all of these ideas because in that discipline, they're referred to as networks. So usually a network refers to a real physical object where a graph can be abstract. So mathematicians, computer scientists usually use the word graphs, whereas engineers use the word networks. And so the analogy between the various parts of a graph are a graph in graph theory is a graph, but in network science, they'd be networks. In graph theory, vertices are called vertices, but in other areas, they may refer to them as nodes, and similarly, edges may refer to as links. So depending on the discipline you go into, you may be using different terminology, but all of the underlying structure and results carry forward. All right, so that's it for this lecture. Basic introduction to multigraphs and some terminology and some proofs. Next lecture, we'll start to explore some more concepts in graph theory. Thanks for watching, and we'll see you in the next lecture.